Ka nui tamahiki a koutou, ko Megan Clune tōku ingoa, he paiwai whakaako ngai o i waipapa taumata rau ki te pūtahi mā tauranga. So greetings to you all. My name's Megan, and as Marla said, I'm a professional teaching fellow at the University in Auckland and our newly renamed and amalgamated Faculty of Arts and Education. I teach across science, maths and technology, and I work primarily with in the primary and intermediate sector, but I also work with postgraduate teachers and supervise master's students as well. But I am also, on top of that, a part-time PhD student, and I am 3 weeks away from submitting. So this is sort of like where I've got to in trying to make sense of everything, and hopefully I make my deadline, but that's another story. So part of my research is escape rooms in mathematics and how we might develop mathematical processes through escape rooms in particular, because I'm particularly interested in how the online space might help us to develop mathematical processes. So the first iteration within my research, I created an escape game called Ye Olde Mathematics Classroom, which was a thematic approach to an escape game, and it just sort of stepped students through a whole range of problems, and I engaged with the student. I observed the students and looked at what processes were emerging and what they were engaged with as they worked through that game. So this all stems from my interest in digital tools, mathematical processes and escape games. I took on a gameful approach to learning rather than a gamification one, because my belief is that gamification, like Lisa was talking about, it sort of applies those external motivators to the learning, whereas a gameful approach relies on the value and the challenge within mathematics to motivate students. So I purposely left off those game components that drive motivation, those intrinsic motivators, and only drew on game dynamics and mechanics that had that were intrinsic motivationally. So in my first digital escape game, the observations I ran the game in lockdown with 4 pairs of students, each playing online in their own homes while I watched them from my own home and recorded all of that. So it was a complex undertaking. But what emerged from that was that students were very much engaged in the process of problem solving. They were doing reasoning. They were using representations, not creating representations. And they were making connections and they were communicating. But however, what I did notice was that mathematical modelling was not present. And I had assumed in the design of the game that I would see mathematical modelling emerge, but that wasn't the case. So what I did then for the next iteration of my study, I wanted to look at, in particular, how the interactions between the students within this digital gameful environment might result in mathematical modelling as the objective activity, and what the game itself actually does in terms of presenting students with challenge and how students respond to that challenge. So I then decided to look a little bit deeper into mathematical modelling because, as you all know, it's not really overt within the early years of the curriculum. It doesn't appear explicitly until later years. Within the new curriculum, it's just sort of absent altogether. The 2007 curriculum had the overarching statement that required students to problem solve and model. So that was throughout the entire curriculum. And then the 2023 refresh, it had aspects within the do side of the curriculum, but now that's all gone as well. But we're not seeing modelling at all in the primary and middle school years. So that is a concern. anyway, so I decided to look at how we could bring modelling sub-processes within into problem-solving contexts for younger students, because a lot of the modelling research doesn't. The majority of the modelling research is targeted at secondary school, and so there is some research, but there's definitely a gap in the research in terms of modelling with younger students. So I drew on Bloom and Lice's schema of the modelling cycle, which you're probably all familiar with, whereby the students engage with a real situation, and then they create a situation model. And throughout the process, they are constructing, they're simplifying and structuring, they're mathematizing from the real world to the world of mathematics. They're working mathematically, then they're interpreting their results that they get in the context of the real world, and then they validate it, and then they expose it. So that was the schema that I was working from. And the definition that I used was from Nice and Heugel, which was to identify and present solutions to real world problems, contexts, and situations using mathematics. So that was the aim. That was what I wanted students to engage with. So I created another game. And this game, I built it by firstly identifying the processes that I wanted to focus on. So the sub-processes of modelling, which were... It's not going to let me go backwards, is it? Which were these ones that I've put in bold down here: mathematizing, working mathematically, and interpreting. So those are the sub-processes that I wanted to focus on. And so I identified those processes. I sourced existing problems or recreated parts of problems and turned them into puzzles, or turns parts of them into puzzles to create a new escape game. So some of the challenges in creating those puzzles were replicating modelling as in the real world process within the classroom, and turning modelling problems into puzzle form. So as you know, a lot of these modelling problems are quite big and they take time to solve, whereas I was just trying to pull out parts that I wanted to focus, that I wanted students to engage with in terms of developing that sub-process. So it was quite hard to turn a very big problem into a smaller puzzle that just focused on a sub-process. So the digital escape game does have limitations in terms of how you can build puzzles within a game, because as you know, modelling problems are often quite open and they're open to interpretation. So you might have one group of students that comes up with one problem and another group of students finding, and another group of students that comes up with another result. And those results depend, you know, within the frame of that modelling problem, they are both equally what we might call correct, you know, justifying their findings. So the limitations of an escape game is that you need correct or incorrect answers. So correct answers allow you to progress, but incorrect answers don't. So that was one of the challenges, a key challenge in creating the game. So I created a second game, which was called the Abandoned Sports Shed. And within that game, there were 5 puzzles, and each puzzle developed a different sub-process or a range of sub-processes. So I had a problem called Kahu's Kayaks, which was focused on making conjectures, reasoning, and validating. For that puzzle, they were required, actually, go back, sorry. I've forgotten where my link is. That's all right. Then the puzzling wallpaper pattern, which developed reasoning, logical thinking, and validating. A puzzle called Through the Window, which was mathematizing, creating representations, interpreting, and validating. So that was specifically creating representations, because in the previous game, I noticed that while students used existing representations, they didn't create their own, or there was limited creation of representations. In the faulty treadmills problem, that focused on mathematizing, working mathematically and interpreting, and the coffee cup conundrum was mathematizing and working mathematically. So as an example, this was an original problem that I got from Enrich. And what I did was very standard in the way that it's written, and potentially students can quite easily work through that. But what I wanted them to do was to engage in a more abstract delivery of it. So I created a video of a treadmill, the sound of a treadmill going, and they had the two, treadmill 1 and treadmill 2. Treadmill 1 was broken, and they had to determine the difference and related to what they were seeing, the information that they had from the video. If they wanted to, throughout the entire game, there were hints and supports in place, so they could optionally click on a button that would provide them the hint. I was also in the room, so they could use me as the teacher. I had the role of the teacher, but I didn't engage unless they engaged with me. So it was very much about them being immersed in the challenge without me imposing myself on their engagement with the game. So if they wanted to, they could click on a hint, for example, with this one, and it would give them, say, a starting point where they might begin in terms of making sense of the problem. Then there might be another hint that they could engage with that would give them, it would scaffold them through how they might approach the problem. So this is the actual problem. So you can see here that they had the option of having the problem in words if they wanted to, and then the hints were down here once they'd played the video. Most students said they didn't want to use the hints because they wanted to see if they could get through it without using the hints. But sometimes when they were really stuck and they looked to me for support, I would say, well, have you checked the hints? So that was one way that that was a common way that they worked through the information. So for this research, I used a design-based research approach in terms of I did 2 iterations, 2 different games, and observed. For the second round, I did it in school and observed students playing in pairs. So they weren't by themselves, they were playing together on a single device. So that I wanted to encourage that communication, that mathematical discussion with students, which is why I put them into pairs to play. The reason for this research, backtracking a little bit, it was a problem of practice in terms of how when I often talk to teachers, when I was teaching, I often would talk to them about mathematical processes. And it was often a point of confusion for teachers because they weren't clear on what mathematical processes were. And I think it was because when I came through my teacher education, I was trained under the 92 curriculum where the processes were very much explicit. And then in my first year of teaching, I was presented with the 2007 curriculum. And so my colleagues who came through under the 2007 curriculum didn't have that explicit understanding of processes that I had from the previous curriculum. So this made me think about how can we make processes more explicit and engage students as well as teachers in designing for engaging the processes. I used Zoom to record all of the instances of all of the groups of play, gameplay, and I used activity theory as a lens for data analysis. So what that meant was, as I analysed the data, the gameplay, I looked for interactions that were happening between the students in the game, the students and each other, the students and me, and the students and the rules of the game. So what I found was that these 4, mathematizing, working mathematically, interpreting, and validating, were the focus of this game. So working mathematically appeared quite a bit. But, well, I guess in hindsight it was expected, but I hadn't actually thought about it before I created the game, but constructing and simplifying were actually the primary sub-processes that were observed. And that makes sense because in order to solve a puzzle or solve a problem, students need to construct their understanding of the problem, and they need to simplify it. So it made sense that they would engage with those the most. Mathematizing, there was limited mathematizing that occurred in terms of what I expected, but students still did mathematize. There was a lot of mathematical working as expected. They needed to work mathematically in order to solve the solutions. Interpreting was limited, and as was validating, and a lot of it was validating was often done by the game itself. So students would use the game to determine whether or not their answers were correct, rather than talking with each other to check whether their answers were correct. So that requires more thinking if I'm going to do another game. But other mathematical processes emerged as they engaged with this game as well. So the using representations was a focus for one particular puzzle, which was, I might be able to find it here if I go here quickly. This one here. So for this one here, they had to, the problem was that there was a small bush X meters from the window, and school hall, which was a horizontal X meters from that bush, and then the height of the bush in the school hall. So they needed to solve it. So these hints, students, most of the students tried to solve things in their head just by taking numbers and trying to work out some sort of result from the numbers that appeared to them. So for example, sorry about the siren going off. I live rurally. So for example, a lot of teachers said, oh, a lot of students said, oh, the answer is 28, because those were the numbers that were presented to them. So the hints specifically encourage them to engage with creating representations and scaffold them through more of a, well, where would you start? And I only encourage them to use the hints if they needed all the hints. If the first hint was enough, then they stopped there. If they needed the second hint, and so on and so on and so on. So that using representations, all students engage with that, and there were multiple versions of the representations that they made. But the representations that they initially made were very much non-mathematical. They were very much still grounded in the real world. And so transferring what they understood of the real world into a mathematical representation was a challenge for the majority of the students. So that was a good outcome. There was a lot of conjecturing and clarifying. The prompting, a lot of the prompting occurred what came from me, in terms of encouraging them to either refer to something or to clarify their thinking or to encourage discussion, things like that. There was probably just as much from me as there was from the students themselves. In terms of selecting tools, so they were given, the game was online and they played it on one device, and they were told that they could use any tools they wanted. They could use Google searches, they could use online calculators, they could do whatever they want. There was no limit in terms of what they could access, but they were very reluctant to use the tools. Some commented early on that it felt like cheating if they were using tools, even though they had been, I explicitly said, you can use whatever you like, there's no limitation. A lot of them, even for things like pen and paper, which I had in the tables, they were reluctant to use that because they thought they had to do everything in their heads. So part of this was really trying to make obvious what are the working habits as well of these students, and what expectations do they have in terms of, how they might make their thinking explicit, and the tools they use when they're working mathematically. So that was very interesting for me. The So by puzzle, as you can see, constructing was very clearly a feature of most of the puzzles. Simplifying and structuring was for over half of them as well. So the puzzles themselves, they prompted use of all the processes that I had aimed for, but to different degrees. And across the game sessions, there was similar engagement for some students, but some groups did one thing more than the other. For example, one session did very little working mathematically compared to others, and another session did more validating than other sessions. But on the whole, the puzzles themselves prompted a whole range of process use. The tricky part is making it explicit that the students are engaging with those processes. So at the end of a game, it's really important to have a debrief time where you go through and you talk about the things that the students engaged with. So do you remember when you were doing this puzzle? And what processes, what were you doing to help you solve that? So making it clear that, they are mathematizing, they are interpreting, and they are working mathematically, and they are creating representations. So in terms of some of the challenges, mathematizing was challenging for students. They as I said, they found it quite difficult to turn some of these real world problems into mathematical, and interpret them in terms of the mathematical world. And there was a high level of constructing and simplifying, which in hindsight should have been expected. As I said, there was a reluctance to use tools. And the amount of scaffolding from me was unexpected. So when I first designed the games, I had thought, they're not going to need me at all. They've got all the hints and all these things that are supporting them. They're not going to need my input at all. But they did. So I think that's encouraging when we're thinking that the digital space might take over our jobs. It won't. No students experienced the game in the same way. So I could have written in a scaffold for a particular group, but another group needed a completely different scaffold. So I don't think it's possible to account for every single need within game design. And as I said, teacher prompting was core. So I wasn't giving answers, I was just facilitating, I guess, being a game master. And so some of the affordances. So it was very much process-oriented problem solving. So ensuring that students had access to these really rich problems where they could just fully immerse themselves in this game, in this problem-solving environment, a mathematical environment. There was the freedom to fail. So I didn't associate points. There were no penalties. There was no time limits, nothing like that. I just said to them, when they said to me, I'm worried about getting this wrong, or are we allowed to do this? And I was just like, do what you want. It doesn't matter. Give it a go. And so that sort of helped them to realize that they could just try things and see where it led them, and they could debate things. I think the game mode eased a lot of anxiety in terms of mathematics. However, a lot of the students that volunteered, because it was very much a voluntary participation. I think a lot of the students that volunteered were likely in the first round, because that was all online during lockdown, they were likely students that already liked mathematics, so or enjoyed mathematics. So very much a very specific group in all likelihood. For the second game, I get a sense that those students who volunteered for that like game environments. So I would like to look more into whether or not this type of game mode can ease that maths anxiety, but that's the sense that I got. It allowed for learner-orientated assessment. So out of watching all these students engage with the game, even though I didn't know those students to begin with, I got a lot of information about any misconceptions, any gaps in their learning, or where they might go to next in terms of their learning. So it was really valuable for me as a teacher to understand my learners and understand their learning needs. Student engagement was surprising. So when Lisa spoke about challenge, and I think someone commented on how we want students to engage in challenge and really see that mathematics is about finding, being, for me, that challenge and that unknown is what excites me about mathematics. And that's something that I want students to grab onto and be passionate about as well, and to grapple with the challenge. So for all these students, what I had initially anticipated was that it would take them about an hour to do the game. And so they all signed up. The vast majority of students went at least half an hour over time. And at the 1 hour point, I said to all of them that, if you want to, we can just leave it there. Otherwise, you're most welcome to stay and keep going. And they all wanted to stay and keep going and persevere. They would go off and get their lunch and come back and continue with the game. So they welcomed the challenge. They weren't put off by the challenge. So when we think that some of these environments try to make things easy for students because we don't want them to have to struggle, but actually they really enjoyed that aspect of the game. Similarly, I think I mentioned that some students didn't want to use the hints, which is why they took long to get through the game, but that was the expectation that they put on themselves. And so using or not using hints throughout a game, again, allows for that student agency in terms of the support that they access. So there is just some of the references that I used, and that's pretty much me, because I thought I'd leave lots of time for Q&A if there was any. I think I'll just comment on some, one other thing is that a lot of the literature talks about how mathematical modelling is too hard for young students. And I think breaking down into sub-processes and approaching it in smaller, and puzzles that are sort of simpler, or puzzles that are younger student learner, or problems, even mathematical modelling is absolutely accessible to younger students. There's a lot of modelling problems that are out there that are common in the early years. So I don't think I know it's not in the curriculum, but I think it's something that we consider about bringing more into our classrooms if we're trying to develop those broader mathematical competencies.
It's sort of balancing everything in the classroom, isn't it? Mm-hmm. And also, what you were mentioning about representations is one of the key things that we want students to be able to, representing the problem in a way that they can actually proceed to investigate and solve it. So those multiple representations give them an idea about the concept. And of course, they need the procedures as well in order to be able to solve. And what do you think about the mathematical language or the vocabulary? How does that fit into the representations in this in the modeling area, Megan?
So you mean like for mathematical communication in general, or using the terminology of mathematical modeling?
Both, right.
Yeah. So in terms of mathematical communication, so that's one thing that I did look at in the first game especially. And again, in terms of assessment, it did highlight for me as a teacher the language that I could develop with students. So for example, in one of the games, they had to use Pythagoras' theorem to find the side of a triangle, right angle triangle. And one of the participants kept saying, well, we need to know, we've got the length of this side, and she didn't have the vocabulary for a hypotenuse. So that was something that I could, as a teacher, develop and extend on. So it provided an opportunity to gauge where students were at, but also to develop their language. In terms of the language for mathematical modelling, it's a similar thing, although I was introducing new words to them in terms of, when you turn this into a real world problem, you were mathematizing, and so that was something that they could then go on and use. But I think it's important that they understand what they're doing so they've got the language to apply to those processes.
You're absolutely right. The communication, the language, the mathematical language, and the specialist vocabulary does support their conceptual understanding and their procedural fluency and problem solving as well. In the end, you're absolutely right. Another thing that you mentioned was the scaffolding, which I think is really important, like whether it's the modeling or what we do, whatever we do in the classroom. And I think that, eases anxiety and as well as supports agency, the scaffolding that you mentioned for both the games as well as for the teaching in the classroom.
Yeah. Just Simone's comment there about commenting on the struggle to mathematize in the modelling process and how we can prompt scaffold. So for when I was thinking about puzzles that were in real world context, so I guess the scaffolds that I sort of look for in terms of mathematizing is to ask students to think about and depending on the age and stage of your learners, it's unpacking what can you identify within that real world problem that might relate to a mathematical version of that problem. So some of the words we might use interchangeably. So, there's sometimes we talk about mathematical representations exist in a variety of forms. So we can talk about, how might it exist as a depending on the age of your students, as an equation or a number sentence, or how might you draw a picture of that using mathematical images, using mathematical representations, using mathematical symbols, and the characters that you know. So it can be tricky, but it depends on the age of the learners that you're working with and how you get them to transfer one to the other. So when I was asking them to represent that through the window problem in terms of mathematics, they already had some symbols and characters and numerals there to work with. And so what I asked them to do was, well, can you represent whatever that is the problem's asking you to do? Can you draw a picture of it? And a lot of them drew a picture of, they drew a lovely tree and a house and all that sort of stuff, but there was no relationship between the two in terms of establishing where these X distances existed and things like that. So I drew their attention to, well, what is this letter telling us? What is this number telling us? What are these symbols telling us? And how are you going to transfer that onto your image? So it's about being explicit in terms of making those connections for them if they're not seeing them immediately. Hopefully that helps.
Did you provide them some examples of what it could be in another situation?
No. Okay. So part of the game was just to throw them in and see what they could do. So and the aim of the hints was if they needed that help, then that would sort of scaffold them through getting to where I had imagined they might be able to solve, my interpretation of the way that the problem could be solved. Probably not the only way, but it was the way that I might work with them had I been just looking at this problem just as a general standalone problem. But I also didn't want to remove the possibility for students to work through these problems in their own ways, which is why I wanted the hints to be optional, and only if they were struggling then to work through the hints in that way.
We have another question here from the chat from James. So did you have students who disagreed with each other and then didn't want to work together to the end?
Very interesting question, James. Short answer is sort of. So the majority for the modeling game, the majority of them didn't, I wouldn't call it disagreeing, I would call it mathematical argumentation. They challenged the mathematical ideas of each other, but they worked together to come to consensus. In the first game, it was interesting because there was one pair of students that were working together on the Pythagoras problem. One student claimed they knew what Pythagoras was and how to work it out, and they were like, oh, just Google this and just Google that, and the other students still couldn't work it out. But the student who claimed they knew what it was about also didn't want to explain to that student. So I suspect that even though they had heard the name of the theorem, they didn't actually understand the theorem. And so the other student went through the hints in order to understand. And what happened was that those students actually worked parallel to each other. So one student was doing one thing and the other student was doing the other thing. And then they came back together with the answer. And they discussed it a bit, and one student got, their answer was correct and the other one wasn't correct. And so the game justified or decided, that they told them which one was correct and which one wasn't correct. And there was a little bit of tension after that, but they quickly got over it and then started working together on the next problem. But I think that's a good thing because, it's helping them negotiate those relationships. And in terms of, okay, I got that wrong, I'm a little bit upset, but I'm going to get over it and we're going to move on and work on the next thing. I do want to say, though, that these pairings were self-selected. So they were working with students that they already knew and working with students that they already had a relationship with. So that may have influenced those outcomes.
Thank you for that, Megan. This is in assumption that the students are working remotely, right? So they're not in an actual physical classroom working together.
That was that the students that were working parallel to each other were working remotely, but the other group of students were working together in the same room. Yeah.
Oh, okay. So it's a mix of those kinds of.
So the modeling game was done with students in the same room. Yeah.
Very interesting question from Heather Lewis. The curriculum now has precise maths vocab students should know at the group year levels, so teachers are planning to teach the precise words to describe mathematics, and also the description of using column methods for operations. Is this part of where mathematical modeling is expressed in the refreshed maths and stats curriculum?
Okay, the first part of that question, I'm a huge fan of mathematical vocab. So, I think the sooner we introduce that language and those words and the terminology, the better. I used to have maths walls with vocabs for my younger students, and I was forever building in vocabulary left, right, and centre. So I think it's really important. So I'm not opposed to teaching mathematical precise words to describe mathematics. I think it's excellent. In terms of column method for operations, no, I don't see that I see that fitting within mathematical working. So modeling is, for me, is much bigger than that. But certainly using something like, I know they have a column methods, and I think there's another area model I think they refer to in the curriculum as well for younger students. But that for me fits within that sub-process of mathematical working. So it's a strategy or a heuristic that students can draw on within working mathematically or within problem solving or whatever it might be.
Maybe I'll just piggyback on that one. Yeah. So I really found introducing mathematical modeling to middle year students, because the impression was we usually, even from the country where I came from, we usually do mathematical modeling in the high school level. So it's interesting that there's a breakthrough for introducing modeling to the lower level students. And what's so interesting about this is it's being gamified. So it's
Mm.
refreshing to attend Lisa's plenary this morning and then this session. And I was like, it's a true testament that as long as the teacher has the control of what tools to use in the classroom without really depending on those tools so much, so chances are students are learning at their optimum levels. So we really thank you, Megan, for really sharing this insight to us. And hopefully in the next sessions, you will also be able to share to us how to actually design the escape game, because I think that that part is the most challenging part, because
It
there's
is.
a lot of things to consider. Yeah.
Yeah, so
Yeah.
games do take a long time to design, but they are my passion. So it's sort of like my happy place. When everything else is falling apart, I go and I make an escape game. So I think, but they're definitely worthwhile. And I'm not a fan of pre-made games. So while I'm happy to share my games, it's not. I don't think that the be all and end that my games are the be all and end all for your students. But I really encourage teachers to make their own games, because you know your students and you know what they need. So that's sort of my view on making your own escape game.